Good morning students, myself Srishti Chaudhary working as lecturer in Electronics and Communication Engineering branch in GPTC Patiala. Today I am again here to discuss upon the topic of receivers, the second part of receivers. We are going to continue here. In the last chapter or last lecture we discussed these following contents, that is the tuned radio frequency receiver, the drawbacks that occur in your tuned radio frequency receiver, that was instability, that was due to the very high frequency that was in tuned radio frequency that provided that your component or the circuit stopped working as an amplifier and it started working as an oscillator. Second drawback was variation in bandwidth. Again it was due to the very high frequency due to which your adjacent channels was picked up. As adjacent channels was picked up, so you are having a poor selectivity in case of your TRF, tuned radio frequency receivers. Next we discussed in the last lecture was super heterodyne receiver that follows your super heterodyning principle, that is the mixing of two frequencies, and that is a non-linear mixing to produce a new frequency component. And the receiver characteristics, that was selectivity, sensitivity and fidelity. Selectivity was to select a desired signal and rejecting all other undesired signals. Then it was your sensitivity. Sensitivity was to amplify the weak signals, that is the minimum signal strength that can be amplified at the receiver input. And at last it was fidelity, that was to reproduce the original signal from the signal you have received. Now in this lecture we are going to discuss following three contents that were left. That was, one is the FM receiver, AGC, that is automatic gain control, and at last you are going to discuss, or we are going to discuss about the communication receivers. Now coming with the FM receivers, we have done what are the receivers. Receivers receives the signal at the input and get them into the original form, that is a demodulation process is done at the receivers. FM receiver also operates on the super heterodyning principle, that is super heterodyning principle is the mixing of two frequencies to get a new frequency component, and this mixing is the non-linear mixing. But the operating frequencies in FM are much higher than AM. In the case of your AM receivers, the operating frequencies was very much less as compared to your FM. FM receivers needed the circuits like limiter and de-emphasis that were not there in the case of your AM receivers that we discussed in the last lecture. But in case of your FM receivers, these two circuits are needed. One is the limiter circuit and second is the de-emphasis circuit. FM demodulators are different from AM detectors. As in case of your AM detectors, you use the detectors like envelope detector, but in FM demodulators the detectors used is, for example, Foster Cele, your Foster discriminator. Now this is the basic block diagram of your FM receiver. Now seeing to this block diagram, it is seen that basic block diagram is similar to that of your AM receiver, but only the difference is that two blocks are added here. One is of this limiter and second is the de-emphasis block that is added to the basic block diagram of the receiver. Other blocks are same or similar that was in the case of your AM receiver. So what is the RF amplifier? RF amplifier selects or pre-selects a particular signal that is desired and amplifies it. Again you are having a mixer. In the mixer you are having the two inputs. One is from the RF amplifier, that is your received signal or signal frequency, and second input is from the local oscillator, that is the local oscillator frequency F0. Mixer mixes these two frequencies. Again you are having a super heterodyning principle here. You are at the output you are having the intermediate frequency, that is F0 minus Fs. We have discussed in the last lecture also that mixer provides you with the four components F0 Fs, F0 plus Fs and F0 minus Fs. With these four components only the difference component is allowed to pass on, rejecting all other components. So F0 minus Fs is your intermediate frequency that is passed on to the IF amplifier. At the IF amplifier the input is your intermediate frequency. This intermediate frequency is amplified by the intermediate frequency amplifier, and after amplification it is provided to the limiter. Now what is the limiter? Why limiter is needed? We are going to discuss it in detail also, but here in a one basic line, limiter limits the unwanted or undesired signal or noise or error that occurs in your FM wave or FM signal. After limiting your undesired noise or error, limiter passes your the signal to the FM detector. FM detector demodulates the signal to its original form so that you get the original signal in its form. After FM detector, you are having the de-emphasis circuit. Now de-emphasis circuits nullifies the artificial boosting of the signal. In your previous semester subject, that was your principles of communication in engineering, you discussed these pre-emphasis and de-emphasis in your AM and FM modulations. Pre-emphasis were provided in the transmitter side, so it was an artificial boosting that was provided to your signal. De-emphasis is provided at the receiver side so that it can nullify the artificial boosting that was provided at the transmitter side, so that it can get into the original signal form. After you get in the original signal, the signal is passed on to the AM FM power amplifier, and at last it is given to the loudspeaker or the load circuit. Now coming into detail, RF amplifier improves signal to noise ratio. It selects a particular signal, that is the desired signal, rejects all other signals and give it to the further mixer, and matches the receiver input impedance to antenna impedance. The mixer is a frequency converter block. You can say that it mixes the two frequencies. One is the signal frequency from the RF amplifier, and second is the local oscillator frequency from the local oscillator block. And it is similar to AM receiver, that is it down converts the received signal to an intermediate frequency. That was same in the case of your AM receiver, but here the tuning range is less than that was in the case of your AM broadcasting. It is 88 megahertz to 108 megahertz, and IF produced at the output of mixer is 10.7 megahertz. In case of your AM receivers, the output of mixer was 455 kilohertz, and the range for the intermediate frequency was 438 to 465 kilohertz. In case of your FM receiver, this intermediate frequency is very large. It is in megahertz. In case of your AM receiver, that was in the case of kilohertz. Now IF amplifier, that is intermediate frequency amplifier, as the name indicates, amplifies the intermediate frequency that was output from the mixer. Mixer output is your intermediate frequency. That intermediate frequency signal is given to your IF amplifier block. In case of FM receivers, IF and bandwidth required are much higher. Both the intermediate frequency we have discussed is 10.7 megahertz, that is higher, and also bandwidth required is very much higher. IF is 10.7 megahertz and the bandwidth is 200 kilohertz. This large bandwidth will produce low gain per stage. You are having the bandwidth more, this bandwidth will in result give you the low gain per stage. So to increase the gain, you need more amplifiers. So more IF amplifiers are required and are cascaded, that is you are having a low gain because of the high bandwidth. To increase the gain, you are cascading the amplifier stages, that is one after the other. In succession you are providing the IF amplifiers so that your gain can be increased, that is reduced to the large IF. Now coming to the amplitude limiter stage that we discussed, why the stage is needed, why you need a limiter stage in the FM that was not needed in the case of your AM. Transmitted FM wave has constant amplitude, but unwanted noise and signal added to it change its amplitude. If you are transmitting a FM wave has constant amplitude, but if an unwanted signal or unwanted noise is added to this particular FM wave, its amplitude varies. Now this amplitude variation has to be removed before it enters to a demodulator block, that is before the demodulation process is being started, this amplitude variations has to be removed. Otherwise distortion appears in your demodulated signal, that is original signal you are going to process. As demodulators react to amplitude changes as well as frequency changes, demodulator will not differentiate between the original signal and the error signal. It will react to both the amplitude changes as well as the frequency changes. So limiter removes all such unwanted amplitude variations in case of your FM receivers. Now why limiter can be an advantage in case of your FM receiver and cannot be used in case of your amplitude AM receivers? The reason is that in case of your AM, when you are considering the AM wave, the signal is contained, or signal or information is in the form of amplitude, and if we provide the limiter in case of your AM receivers, it will limit the amplitude. If amplitude will be limited, your signal will be distorted, you are having a distorted signal at the output. But in case of your FM receivers, the signal you are going to process is a FM wave, that is a FM signal. In a FM signal, the information or signal is in the form of frequency, it is not in the form of amplitude. So you limits the amplitude variations, but your signal is not distorted, you are not affecting your signal that is contained in the frequency form. So the your signal is in not affected by this limiter, only the amplitude variations that were unwanted noise or signal that is limited by this limiter stage. So your signal, original signal you are going to be processed, it is not a distorted one. That's why this limiter stage cannot be used in the case of your AM receivers, it is used in the case of your FM receivers. Now, de-emphasis circuit, we have discussed that de-emphasis circuit is installed at the receiver side, pre-emphasis was there in the case of your transmitter side. Why the de-emphasis circuit is needed? Artificial boosting that was given to a higher modulating frequencies. In the process of pre-emphasis at the transmitter side or at the transmitting end, has to be nullified to get the original signal into the form. So de-emphasis circuit provides that artificial boosting should be compensated, that is the artificial boosting that was provided at the transmitter end should be nullified or it should be compensated to 0 so that you can get the original signal into its form. De-emphasis circuit is used after the FM demodulator, that is after you have demodulated the signal, you are having the original signal, after you are having a de-emphasis circuit that will provide that artificial boosting of the signal is nullified, you have compensated the artificial boosting that was provided at the transmitting end. This was about the FM receivers. Now in the last chapter we discussed about AM receivers, now we have discussed the FM receivers. So we can have a short differentiation between the AM and the FM receivers. AM receivers frequency range is 540 kHz to 1600 kHz, but FM receivers frequency range is 88 MHz to 108 MHz. The detectors in case of your AM and FMs are different. AM detector basically uses the envelope detectors. In FM, demodulator basically a frequency to amplitude converters are needed. Foster-Seeley is commonly used as a detector in case of your FM receivers. No limiter and de-emphasis stages were there in the AM receivers because there was no artificial boosting in case of your AM wave. So no limiter, no noise was added in case of your AM receiver, we considered that. So no limiters and no de-emphasis circuit was there in case of your AM receivers. But in case of your FM receivers, you are having the blocks as limiter and as de-emphasis. The intermediate frequency in case of your AM receiver was 455 kHz and the range of your intermediate frequency in case of your AM receiver was 438 to 465 kHz. But FM receivers, the range is very much high, that is in the megahertz. So intermediate frequency in case of your FM receiver is 10.7 megahertz. For AM radio, each station occupies maximum bandwidth of 10 kHz. In case of your FM radio, each station occupies a maximum bandwidth of 200 kHz. That is also very much greater as compared to your AM receivers, that is only 10 kHz, but in case of your FM receivers, it is 200 kHz. In case of your AM, your transmission bandwidth, that is BT, denoted by dBT, is equal to 2 omega. In case of your FM, the transmission bandwidth, that is BT, is 2 d plus 1 omega, that are Carson's rule. The input signal in case of your AM receiver is your AM wave, but in case of your FM receiver, the input signal is the FM wave. Now coming to your next topic, it is the automatic gain control. As the name indicates, automatic gain control controls your gain of the circuit you are operating on. Why the controlling of the gain of the circuit is needed? The basic criteria for this, that you are assuming that at the input, at the receiving end, you are having number of signals, there are various signals present at the receiving end, but that various signals cannot be of the same strength. Some signals are weak and some signals are going to be the strong signals. So we want a constant at the output. For the constant at the output, the gain of the signals has to be controlled or it has to be compensated. So weak signals are operated with the high gain and your stronger signals are operated with the lower gain, so that you can have one constant at the output of the circuit. So signals receiver receiving at the receiver input are not of the same strength. Signal of strong stations are strong and the signals from the weak stations are weak. If receiver gain constant, if we want that the receiver gain should be constant, then receiver output have to fluctuate, and this fluctuation is proportional to the input signal strength, which is not desired. We don't want that your our output should fluctuate with respect to your input. We want a constant output at the output of the circuit. So AGC provides this control. AGC adjusts receiver gain automatically to have constant output. That is, there is no fluctuations at the output with respect to your input. That is adjusted by using this automatic gain control irrespective of the input signal strength. Input signal strength can be of strong signals, it can be of weak signals, but it is compensated by your automatic gain control adjust. The types of AGC, we are having simple AGC, delayed AGC, idle AGC and no AGC. No AGC means you are not providing any automatic gain control to your circuit. Idle AGC means that up to a particular point you are having the AGC provided, and you are not providing the AGC. After that particular point, the AGC, that is automatic gain control, is provided. Delayed AGC is similar to idle AGC. It is just that the point is adjustable at which you want that AGC should occur, after that or not. Simple AGC provides the automatic gain control for all the signals, that is for weak signals as well as for the strong signals. These AGCs will be much clear by this diagram. Here you are having two axes. We are showing the types of AGC with the axis diagram. At one axis you are having the receiver output voltage, and the x axis you are having the strength of incoming signal. Now here no AGC means that you have not provided any automatic gain control to the circuit. There is no feedback from output to the input for the variations or fluctuations that are occurring at the output of the circuit. In case of your simple AGC, you are providing the automatic gain control. Now this AGC is provided for both signals, that is strong signals as well as your weak signals. This is so a simple AGC has one disadvantage is that it attenuate your weak signals also. Now this graph is your for idle AGC. Here this point, that is up to this point OA, there is no AGC provided. After this point A, you are having the automatic gain control, that is for stronger signals than the point A, you are providing the automatic gain control in the circuit. Delayed AGC, it is at the point this B. This point B is adjustable. You can adjust this point B as per your requirement. It means that signals you think are stronger, for which you needed the AGC to be provided. After this point B, the AGC is provided. Below this point you are considering that they are weak signals, so you are not providing any automatic gain control to that weak signals. But after this point B, you are considering that there are stronger signals. For that stronger signals you are providing the automatic gain control. Now simple AGC, it will change overall gain of a receiver automatically. Now overall gain of a receiver automatically means that we have discussed, it will change the gain for both the stronger signals and for the weaker signals itself. Thus it keeps receiver output constant even when input signal strength changes. If your input changes but the output of the circuit is constant, you have providing the simple AGC. Receiver gain is automatically reduced as input signal becomes stronger. You are having the reduced gain as your signal is becoming stronger and stronger in case of your simple AGC. So advantages in case of your simple AGC is its simplicity, it is simple to construct, it is low cost. The disadvantage is that simple AGC is provided for both your weaker signal and for the stronger signal as well. So weak signals are also attenuated, that is not needed. We don't want that weak signals should have the lower gain, but here the weak signals are also attenuated. This is the disadvantage in case of your simple AGC, that is not required. The application of your simple AGC is low cost domestic radio receivers. They are used in case of your low cost domestic radio receivers. Now idle AGC, as we have discussed in the diagram also, for portion of OA, that is for weak signal, no AGC is applied. Considering the point, a predetermined point level A, up to level A there is no AGC provided. You are considering that up to the level A there are weak signals, and that weak signals don't need any automatic gain control. After point A, AGC is applied, that is keeping receiver output constant. Thus there is no gain reduction for the weak signals in case of your idle AGC, but there is the gain reduction for stronger signals in case of your idle AGC. Now coming to the delayed AGC, in this case it is the similar to your idle AGC, just the point here is adjustable. In case of your idle AGC, the point A was not adjustable, but in case of your delayed AGC, the point that is a predetermined point or level that is decided by yourself, so that you can consider that signals before that point are weak signals and signals after that point are your stronger signals. You provided the AGC for the stronger signals, not for the weak signals. In this case, AGC bias is not applied until input signal strength reaches a predetermined level point B. This predetermined level point B is adjustable, that is, this point can be adjusted by yourself. After this point is reached, AGC bias is applied, that is, after this point B is there, it has been reached, the AGC bias is applied, that is, you are having the automatic gain control process being started, like it was in the case of your simple AGC, but here it is processed more strongly. Thus reducing receiver gain for weak signals is avoided in case of your delayed AGC. Now coming to the operation of your delayed AGC. In the case of your delayed AGC, now this is the basic circuit diagram of your delayed AGC. From the last IF amplifier, you are having the amplifier stages. The output of your last IF amplifier is given to this practical diode detector circuit. This practical diode detector circuit processes your strong and weak signals appropriately, so that the gain can be reduced or increased as per desired requirement. For stronger signals we want to reduce the gain, but for the weak signals we don't want to reduce the gain. Here in the diagram we are having two diodes. One, this is the detector diode, and here this is the AGC diode, that is automatic gain control diode. This AGC diode provides the working for the reduction of gain for the stronger signals, that is, whether the diode is forward biased or the reverse biased, it provides that whether the gain will be reduced or not. Now here an adjustable positive bias is applied to cathode of AGC diode. Anode of diode is connected to the output of last IF amplifier, as I have shown you that your anode of diode is connected to the output of last IF amplifier through a coupling capacitor CC. The filter is R3C3, it filters out the high frequency that is appearing at anode of AGC diode. When input signal is weak, then anode of AGC diode is at less potential than cathode, so it is off. Here consider this, you are having this AGC diode. When your input is weak, it is coupled to this coupling capacitor. When you are having a input at less potential, this diode will be off, because it is having at the less potential as compared to the high potential, so your diode will be off. If the diode will be off, the output of your AGC diode will be 0, that is, you are not providing any gain reduction for your weak signals. And this point, predetermined point level B, is desired by yourself, that you have decided the predetermined point level B. For that predetermined level B, below that particular potential, that is less than potential of B, this diode will be off. So output of your AGC diode will be 0. After you are having a high potential between your anode and cathode, this diode will be working, that it will be forward biased. After this diode is working, you are having a constant output voltage, that will be VB plus VT, that is the bias voltage plus the diode voltage. A constant voltage is provided for every stronger signal after the predetermined level point B, and that is given. So you are providing a reduction in gain for your stronger signals. So AGC output was 0 when your potential was less. When input signal is strong, then AGC diode is forward biased, as I have discussed. So AGC output will be constant you are having a constant voltage, that is bias voltage plus the diode voltage, AGC diode voltage. Thus delayed AGC reduces gain for only strong signals and not for the weak signals. As we have discussed, for weak signals you are not providing any AGC, your diode is off for the weak signals as the potential is less. But for your stronger signals you are providing the AGC, your diode is forward biased, you are having a constant voltage VB plus VD. For each and every stronger signals that are greater than the predetermined level B, automatic gain control is provided, that is the gain is reduced. We can say characteristics of delayed AGC is similar to idle AGC that we have discussed, that in idle AGC also you are having a point level A. For OA you were not having any AGC provided to the circuit, after the point A you were providing the AGC. Similarly in delayed AGC you are having a predetermined level B. Up to that predetermined level B you are not having any AGC, after that predetermined level is achieved you are going to have the AGC. But the difference between your similarities between delayed and idle AGC, that you are not providing any AGC below that predetermined level. But what is the difference between the idle AGC and delayed AGC is that in case of your idle AGC, the OA point, that is the A point or A level is not adjustable, but in case of your delayed AGC, the predetermined level B is adjustable. You can adjust that particular point B for stronger or weaker signals. That is, you can consider some signals to be stronger, some signals to be weaker. According to that, you can have a predetermined level labeled as B, that for particular that point there is no AGC, after that point is achieved you are having the AGC. But here we can adjust point B by adjusting delay adjust potentiometer, that is seen in the diagram also. Here you are having the adjust potentiometer that adjusts your point or predetermined level point B. So advantages of your delayed AGC is that weak signals are not attenuated, that was in the case of your simple AGC. In your simple AGC both weak and strong signals were attenuated. Disadvantages are that it is complex than your simple AGC. Applications, it is used for high quality communication receivers, and this communication receivers is our next topic to be discussed. Communication receiver, also known as your double conversion receiver. This is the basic block diagram of your communication receivers. Here you can see that you are having two mixers. First, this is the first mixer and this is the second mixer, both having a oscillator connected to it. So one input of the mixer is from the oscillator and second is from the RF amplifier. In your last chapter we discussed about the choice of intermediate frequency, that your intermediate frequency is value of intermediate frequency is a trade-off between a high value of IF or a low value of IF. Both have their pros and cons. One had poor selectivity, one had better selectivity, one had poor image frequency rejection ratio, one had better image frequency rejection ratio. So we needed the both, we needed the better selectivity, we needed the better image frequency rejection ratio. So for both the requirements, for the pros that we needed from your high IF and low IF, so there is a trade-off between the value of the intermediate frequency or the choice of intermediate frequency that we needed. So in the communication receiver, this choice of intermediate frequency is the basic function for your communication receiver, that how you are processing the intermediate frequencies here. Now reason for using double radio receiver, that is why you are using the two intermediate frequency in case of your communication receiver, that is your double conversion receiver. When choosing the intermediate frequency for a super heterodyne radio receiver, there is a trade-off to be made between the advantages of using low frequency and high frequency. I have discussed that you are having a trade-off. You needed the both better selectivity and you needed the better image frequency ratio, but both have is can be related to one high IF and one is related to the low IF. So considering your high frequency IF, while we are using the high frequency IF, the use of high frequency IF means that the difference between wanted frequency and the unwanted image is much greater. that is desired signal frequency and your unwanted signal difference is very much greater, and it is easier to achieve high levels of performance because the front end filtering is able to provide high levels of rejection. So you are providing the high level of rejection, that is you are having the better selectivity in this case. Now considering your low frequency IF, the advantage of choosing a low frequency IF is that filters that provide adjacent channel rejection are lower in frequency, and the